Hey y'all, today we're going to look at one important calculation stemming from our equilibrium expressions that will often be utilized as a way to determine how strong a weak acid or weak base are. It's the percent ionization. Percent ionization is one more way that we can use the Ka value and our Rice tables to be able to do some math associated with acid-base equilibrium. So let's get started by looking at the equation for percent ionization and then talk a little bit about what it's going to show us. Percent ionization takes the concentration of your H plus and divides it by the initial concentration of your weak acid. Okay. For a weak base, it would be takes the concentration of OH minus and divides it by the original concentration of your weak base. In both cases, we then multiply by 100 to get to percentage. Essentially, the way we can think about this is in the same way we think about money. If I have $10 and I give you $1, I have lost 10% of my money. In other words, I've lost 1 out of the original 10 that I had. It's a little different than the last video where we had to use a Rice table, subtract out the X, and perhaps account for the X. In this case, we're not doing that. We're not accounting for how much has ionized in that denominator. So again, let me repeat. It's the at equilibrium concentration of H plus or OH minus divided by your original concentration of weak acid or weak base. In almost every circumstance that you're going to be put in this year, we're going to be looking at the percent dissociation or percent ionization of a weak acid. Even though you can use this for weak bases, we're actually not going to really address that here just because it's so rarely seen. But in the end, you're going to do the exact same thing as you would with a weak acid, but you're just switching the H plus for the OH minus. It's important to note that we only use percent ionization in weak acids or weak bases in the same way we only use Kas and Kbs in weak acids and weak bases, because strong acids and strong bases are considered to ionize 100%. So their percent ionization would be 100. Obviously, for weak acids and weak bases, it will be less than 100%. Let's go ahead and get started with a practice problem. We want to find the percent ionization of this acetic acid solution that has a concentration of 0.1 molar. We know the Ka of acetic acid is 1.75 times 10 to the negative fifth. So what we're going to do is we're going to approach this just like the x squared problems of the last video, where we start with the initial value of your acetic acid of 0.1 and the initial concentrations of your weak base conjugate, acetate, and your H plus are going to be 0. This is going to go down by X. These are both going to go up by X, which means at equilibrium, we end up with this equaling 0.1 minus X, and each of these equaling X. The first thing we need to do now is find X. In order to find X, we're going to plug into our equilibrium expression. I'm going to ignore the minus X here because remember in the last video, as long as it's less than 5%, we ignore it. We don't know if it's less than 5%. So initially I'm going to solve for it, make sure it's less than 5%, and then I'm good. Set up my equilibrium expression. My Ka is 1.75 times 10 to the negative fifth. That means my X value is 1.32 times 10 to the negative third. So that's going to be my concentration of H plus of my CH3COO minus, all right? And because 1.32 times 10 to the negative third is less than 0.1, I don't have to worry about that minus X still, okay? Now, remember, the point of this problem was to find the percent dissociation or percent ionization. What I'm going to do is I'm going to take this X value. I'm going to then divide by the initial concentration of my acetic acid, 0.1, and then multiply by 100. That means that we are 1.32% dissociated. So this is how we solve using the concentration, the initial concentration of our weak acid and the Ka value to find our percent ionization. All right, so now let's look at a second practice problem. In this case, I'm given some different variables. Here I'm given the pH and I'm given the initial concentration, but I'm not given a Ka value. It's still acetic acid. All right, so for a moment, let's forget the Ka value from the last problem. And what we're going to do is we're going to find the percent ionization given what we have. Again, it's all about utilizing the Rice tables in the way we need to. All right, thinking that X is equal to the concentration of H plus, and we have an initial concentration, what we need to do is solve for X, or H plus ion concentration. Because I have the pH, I can do that fairly easily. 10 to the negative pH is the concentration of H plus. In this case, 10 to the negative pH is equal to 4.07 times 10 to the negative fourth moles per liter. I'm then going to take that number, that X, that concentration of H plus, divided by my initial concentration of my weak acid. And in doing so, I'm going to be able to solve for the percent ionization. So I take that value, multiply it by 100, and I get 4.07%. That means that this acetic acid solution has a percent ionization of 4.07%. One thing you might have just noticed in the last two practice problems is the fact that the acetic acid had two different percent dissociations, even though it's the same acid. So what gives? Well, in the first problem, the percent ionization was lower, and the second problem, the percent ionization was higher. And the reason for that is because percent ionization varies with the concentration of our weak acid. As the concentration of the weak acid gets smaller, the percent ionization gets bigger. So if you look at our second practice problem, the percent ionization was almost 4 times greater than in the first problem. And the reason is because the second problem, the acetic acid solution, was diluted by a factor of 10. If we were to continue calculating percent ionizations for different concentrations of acetic acid, you can see in this table exactly how it varies. The reason is because percent ionization is predicated on the value of X, and the value of X is predicated based off of a Rice table, and a Rice table is not a linear thing. Remember, it's X squared, so it doesn't vary in a linear way. So as your percent ionization is going to go up, it's because your concentration has gone down, and as your concentration goes up, your percent ionization is going to go down. One thing this relates to is going back to gas laws. Remember in gas laws, when we increase the volume of a cylinder, we favor the side of the reaction that has more moles of gas? In this situation, what we're really looking at is favoring the side of this reaction that has more moles of aqueous stuff. The right side of this equilibrium system, which is the H plus and A minus, has 2 moles of aqueous stuff, whereas on the reactant side, the original weak acid only has 1 mole of aqueous stuff. So as we dilute it, because of a Le Chatelier type shift, we are going to favor the forward direction. This means more molecules of our weak acid are going to dissociate as the reaction shifts further and further and further to the right. As we dilute, our Q becomes less than K because the X squared on the top has a bigger role than the single term on the bottom. So again, this is very similar to how we approached it with gas laws. We can approach it in a very similar way with aqueous solutions. A dilution favors the side of the reaction with more moles of aqueous stuff. All right, so let's put this in practice. Here's a conceptual type question. I'm not asking you to solve for percent ionization. I just want you to tell me right off the bat which of these 4 options would have the highest percent ionization. Now you'll note that all 4 of the acids are the same. So it's not about species or strength of acid. Instead, it's about dilution. Remember, the answer here is D. And it's because of the fact that it's the lowest concentration, which means that our Q would be less than our K more dramatically, and therefore the reaction would shift further to the right towards those ions. The lowest concentration has the highest percent ionization. Let's take a look at a second problem. All right, which of these would have the lowest percent ionization? Did you pick B? See, here's a trick, because remember, HI is a strong acid. No matter what concentration it's at, we assume that it dissociates 100%. So here the answer has to be either B or D. And the reason it's B is because it's the highest concentration of my weak acid, hydrocyanic acid. So when I look at HCN versus HCN, if I want lowest percent ionization, I'm going to pick the highest concentration, because the higher concentration would shift the reaction closer to the left side in this case, and as a result, percent ionization would go down. That wraps up today's video. Today we looked at percent ionization, how to solve for it, and predicting how it varies with relative concentration. Remember, weak acids and weak bases are in equilibrium, which means things like percent ionization are predicated on equilibrium expressions. Remember, we can use Rice tables to be able to solve for concentrations of H plus or of OH minus. We can use those then in our percent ionization equations, which again, it's really important to keep these two equations separate. They look similar. The Ka expression, percent ionization equation, they look similar. But percent ionization, if you remember, is going to equal the concentration of H plus or OH minus divided by the original concentration of your weak acid or weak base multiplied by 100. Once we solve for that percent ionization, it tells us the relative strength of the acid, but it also tells us relative to the concentration. The higher the concentration, the lower the percent ionization. The lower the concentration, the higher the percent ionization. Today's video was written, directed, produced, and edited by Sean Tao and Jeffrey Pan. Thank you all for watching. I hope you enjoyed it, and I'll see you in the next one.